I got the power. Dun, 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 dun. The definition of power in statistics is when the alternative is true, the ability to reject the null. So can you correctly tell when the alternative is the truth? How would we determine the value of the power itself? Let's make up some null hypothesis that we believe mu is 10. This gives us a value that we can do math with. I want to make this one-sided, so I'm going to say mu is greater than or equal to 10. That way my alternative is going to be left-tailed here at less than 10. If we assume the alternative is true, well, what value is mu? We need to have a value of mu to be able to talk about things. And here it's just less than 10. Is it 9? Is it 8.5? Is it 7.263? Well, keep in mind that question. Let's pick a value in this alternative of just 9. And we'll figure out the answer for 9. And once we know how to do that, we'll come back to how would we do it for all the values that are less than 10.
There's too many of them.
We're going to need a standard deviation, our sample size, and an alpha. But people often do this before they actually gather data. So we don't have an X-bar. We're not going to finish out the hypothesis test. We're just going to talk about how much power there would be. Notice I'm using sigma, so I'm going to be using z-scores. If you're thinking, could we use S and talk about t-scores? Well, that's possible. Computers can do it, but by hand it's a lot harder. So we're just going to stick with the idea of calculating power using z-scores. This means I'm going to have two different pictures. One picture drawn by the null hypothesis. It's centered at 10 with a standard error of 2 over the square root of 36. And there's a rejection region that I've shaded here in black, which is 5%. And we're actually going to figure out where this hits on the number line in just a minute. There's a second picture drawn by the alternative here, which is on the same number line, but it's a shifted over picture, centered at a value of 9, because that's the value we're going to play with first. And it has the same standard error of 2 over the square root of 36. And these are the two competing kind of models we're talking about.
Huh?
This town ain't big enough for the two of us.
What?
On this number line, there's a spot. It's called the critical spot. And if our X-bar lands on this side of that spot, when we do our hypothesis test, we're going to say, oh, we got a p-value bigger than alpha, failed to reject the null hypothesis. If our X-bar lands on the other side of this critical line, then we're going to say, oh, we're in the rejection region, and we need to reject the null hypothesis. When we talk about power, we're saying the alternative is true. So we are rooting for the red team. We want to be on this side of the line. We want to end up rejecting. And even though this line was determined by the black graph based off the null hypothesis, the true probabilities come from the true graph, which is the alternative. So what's the probability of being in the rejection region? It's based, as far as probability, off the red curve. So shading in this region would tell us the power. So here's the steps we're going to do. We're going to look only at the black curve and try to figure out where this line is. And we're going to figure out where that line is using this tail probability on the black curve. Once we know where that line is, we don't need the black curve anymore. We're going to forget it and then think only about the red curve and say, what's the probability of being this far over?